This is a comprehensive paper review of the paper Transformer Memory as a Differentiable Search Index. This paper is pretty crazy. It takes an entire dataset and puts it into the weights of a transformer. Essentially, it trains a search engine not to search through documents, but just to give you the index of the document that matches your query. Just like that, boom. So this video is a comprehensive review of the paper. I'll explain to you what's in the paper, what it's about, and by the end of the video, you should have a good idea of the paper itself. The next video, which I'm going to release tomorrow, will be an interview with the authors. We'll dive right into the content and any criticisms and questions that I raised during the review. As always, let me know what you think in the comments. So now let's get into the video. See you around. Does your company have a lot of people labeling data? Why would you leave such an important task to closed source systems or self-implemented things? Training data is your most valuable asset, and human labels are really expensive. Today's sponsor is Diffgram, which is an open source platform centered around training data. They handle everything to do with training data, especially collecting, labeling, serving, and more. And it is open source, so you can self-host all you want. But there's one cool thing if you let them host it for you, and that is unlimited pricing. No per label annotation, no expensive servers to run. You pay once, you get as much as you want. So thanks again to Diffgram for sponsoring today's video. Check them out using the link in the description to let them know that I sent you. Alright, let's get into the video. Hello there. Today we're looking at Transformer Memory as a Differentiable Search Index by researchers of Google Research. This paper on a high level takes a search problem where you have to index documents and retrieve them, and it puts all of the corpus essentially into the weights of a transformer. So it takes the corpus and trains the transformer, and then at the end they can just give a query to the transformer, and the transformer will output the ID of the document that matches. And it turns out for some datasets that they have, for some settings, and with some clever training and representation of the documents, that can actually work, which is really crazy. This kind of speaks to multiple things, such as obviously our ability to overfit on stuff, but there is some generalization here, as we'll see. On the other hand, also the kind of inner workings of these transformers. And lastly, what's pretty cool is that this is completely, as it says, differentiable. It's a differentiable search index, which means that this can be part of larger neural network architectures because it is fully differentiable, and it can be trained essentially end to end at once. And that means we can potentially employ reinforcement learning agents with kind of retrieval abilities and much more things. So we'll dive into the paper, we'll see what it's about. The idea, as I said, is pretty simple. If you like content like this, then as always, leave a like and tell me what you think in the comments. That's always super helpful. So, as I said, they take a search problem, and the search problem is essentially, I have a corpus, like I have a big database of documents, right? Here is a document, here is a document, and I want to build an index. And an index is some kind of data structure, some kind of thing, and at the index I can throw a query, and the index will return to me an ID, a document ID that specifies which document matches my query. Usually this is done via inverted indices, so I want to tokenize my documents, split them into little tokens, which are usually words or subwords, and I want to stem them and lemmatize them and whatnot. Then I build a reverse index, so for every word, like in, the word in, I remember which documents it appears in, like document 3, document 5, document 11, and so on. And then once the query rolls in, I simply tokenize it as well. I go look into my inverted index and I look up all the documents. And then there's also a ranking step, which means I have to now determine which of these documents is the most relevant. And that is usually done via techniques like TF-IDF features. There is a famous technique called BM25, which is also a baseline in this paper. So this is the classic search kind of way of doing search. If you use any search engine at all, this is being done in the background. for the most part. Newer search engines are catching on. There's neural search and so on. But BM25 is still one of the most performant things that text search has available, and also other types of search. However, there is a new push in sort of neural search. And in neural search, you're trying to take your data set, and for each document, you try to map it to some sort of a vector in vector space. And then once the query comes in, you also map the query to a vector. And for example, you compare inner products. Whichever inner product is largest, that's the document that's relevant. This is just one way. This is what we usually call a bi-encoder method, where the documents in the queries are both mapped individually. So there would be an encoder here, and there would be an encoder here. They all would output one vector, and then the vectors are compared. This could be the same encoder or different encoders for documents in query. This is just one method. There's various methods such as cross encoders, re-rankers, dense retrievers, you name it. However, this method here is different. So what we want to do is we want to take the corpus as such and map that somehow into a neural network. And we're going to talk about this somehow. But we're going to train a neural network. Essentially, how do we represent this? Let's represent it with its layers, such that when later I feed a query to the neural network, as I already said, the ID of the document is the output of the neural network. So it doesn't output a vector that I then go and compare. I don't have to go and feed in query document pairs and then I get out a score of how well they fit together, which I would do in a cross encoder. No, the transformer in this case, the neural network, directly gives me the ID of the document, without seeing the data at inference time. So during training, all of the data has to be mapped somehow into the weights of the neural networks, right? So somewhere in these weights, that information is stored of what the documents are. So the entire corpus is in those weights. And once I enter a query, the correct document ID can only be output, obviously, if the transformer has somehow learned what is in those documents. So that's the setup. It's a pretty simple setup once you kind of see what's going on. It's like a meme, right? We've been trying to neuralize search, and we've still done this two-step process where we train these encoders, but then the actual search is still done using, for example, a nearest neighbor algorithm like here. But this is just the idea of, well, why don't I just ask the neural network to output the result, right? The resulting doc ID. Why don't I just do that? And it turns out that can work surprisingly well. So you can do a couple of things here, but that's essentially it. They say right here in the introduction, they use a sequence-to-sequence learning system to directly map a query to a relevant document ID. They have different corpuses where they train it on. On the smallest corpus, this method improves the hits at 1, which means that whether the top hit is the correct one, more than 20 points, from 12.4% for a dual encoder. So the baseline here is a dual encoder, what I shown whenever there are two encoders and they each output an embedding, to 33.9%. That's a giant gain, right? That's like a 2.5x improvement. However, on a corpus that's 30 times larger, performance is improved by nearly 7 points, which is less. It's also respectable that performance is improved at all. However, I want you to notice, and that's already kind of the first indication, a little bit of obviously what's going on here. On smaller data sets, this method does super duper well. On larger data sets, the method doesn't do that much better than a sort of cross encoder type setup. Sorry, a bi-encoder type setup or a dual encoder type setup, which is understandable, right? Because the smaller the data, the easier it is to absorb it all into your weights. If the data gets larger, that obviously gets harder and harder. There's more data to go around, which means there's more room for error, for confusion, and so on. And a classic search engine or a dual encoder is going to have a easier time in that case. But still, it's a cool paper. It's just that it kind of gets worse with the dataset scale. It does get better with the model scaled, though. The really exciting thing is something that I've already mentioned, and they mention this here. All aspects, sorry about that. They say all aspects of retrieval are mapped into well-understood machine learning tasks. So for example, indexing, which is building the reverted index, or even if you have the dual encoder, you need to build the nearest neighbor index, which is a hard task in high dimensions, is now a special case of model training. So it's just training, and incrementally updating an index becomes just a special case of model updating. So all the tasks are just tasks that we already understand from neural network training. So here is a comparison of the dual encoder method, which is the, let's say, old classic neural search method, not the BM25 retrieval, but the neural search method, and this DSI, the differentiable search index. So in the dual encoder method, what we do is we train this encoder, and in this case, they train one encoder for both the queries as well as the documents. And what we try to do is we are going to try to use some form of contrastive loss. If we actually have query document pairs, what we can do is we can try to get the documents, the query and the document that go with each other to be close together, while making the documents that are unrelated to each other be far apart. So this is some sort of contrastive loss. Obviously, at inference time, what we're going to do is we have a query, we put it through the encoder, we get its embedding, and we do a maximum inner product search through our entire vector space of our indexed data set, and we get a ranked list. So it's kind of this two-step approach with building these indices in between, and with a training objective that is not directly what we want. It is a proxy objective because of the algorithm later needs it, the inner product search, but it is not actually what we want. So let's just train what we want. In the DSI, in the differentiable search index, I simply feed my query along with, I simply feed my query essentially to, in some form, to the system, and the system outputs directly which document is relevant for the query. So the way they train it, and this is one way they train it, is where they feed in queries and documents into the system. So this is an encoder-decoder setup. In fact, they use, I believe, a T5 setup, if I'm not mistaken. So it's a sequence-to-sequence task. They feed in the queries and the documents, and they always output the document ID. So if they feed a document, they just output the ID of the document they fed in. And if they feed a query, they output the ID of the document that the query would hit. So this is, if you have supervised data, you can train the system already for given queries to output the correct document. However, the method also works in what they call zero shot, which is if you do not have any queries, you simply input documents into the system, and then you train it to output the ID of those documents. And you hope that, because the models were pre-trained on language modeling and on various other tasks, you hope that through that, if you then enter a query that kind of describes the same thing as the documents, that the system would still output the best document ID. I mean, after all, it's constrained to output document IDs in most cases, and therefore it needs to give you something, so it might as well give you the thing that is related the most. So that's the reasoning behind it. I've talked a lot about the different parts now of the system. The write-up is actually pretty good. I can recommend reading this paper from top to bottom because it goes in a very structured form into what they investigate. They investigate a lot of engineering choices, which I really appreciate in this system because there are a lot of ways to do this, and not one or the other is not necessarily correct. So they say we explore a number of variations of the DSI architecture. They explore how do we represent documents as such. The naive approach, they say, is just to index the full document. So just input the text as such, like you can see right here, just input the text into the encoder, output the document ID, that's it. But maybe that's not the best thing to do. Maybe you can throw away stop words. Maybe you can do bag of words representation. Maybe something is better than just inputting the first L tokens of the document. Turns out it's not, but it's a good thing to investigate. Then how do we represent document IDs? The data sets, they usually just have like some unique identifier per document. In this case, it's like doc 137, and here it's doc 456. If we do this as a sequence to sequence task, maybe we can do something smarter. Maybe we can give the document IDs some sort of hierarchical notion. They investigate that too. And lastly, they investigate how should we index stuff. So how should the indexing step, this training, go? They also do a lot of ablations on sort of the effect of sizes, the effect of model size and corpus size, and we're going to look into that as well. So the method is called, as I said, differentiable search index. The goal is to fully parameterize traditionally multi-stage retrieval then rank pipelines within a single neural model. And that encompasses two operations. First is indexing, and then the second one is retrieval. In the DSI, we've already discussed this. Indexing is a sequence-to-sequence approach that takes document tokens as input and generates identifiers as output. That is indexing. It's training on the document collection to output their identifiers, and optionally fine-tuning with labeled query sets, labeled query doc ID pairs. The retrieval is then achieved by simply autoregressive generation. I input something and I see what document ID comes out in the sequence-to-sequence model. So it couldn't get easier than that. Let's look a little bit into the engineering choices they consider. First, the indexing method. The first indexing method is what they call inputs to target, and that is probably what I've described so far, which is the sequence-to-sequence task of document tokens maps to document ID. So they input the tokens of the document and they output the document ID. That is the simplest method, the straightforward method from what we've heard so far. And as far as I've read in the paper, as I understand it, this is also what works the best. However, they proclaim that in this way, the only ever output is the document ID. There is no sort of language learning or anything like this. You fully rely on the pre-training for language understanding. That is what they claim here is a potential weakness. And other methods are, targeted at in sort of leveraging or making that weakness go away. They have this targets to inputs method, which they say we could also, at training time, what they call indexing time, input a document ID and then have the model decode the tokens of the document. Now, this might seem a bit weird because it doesn't train the model to produce document IDs from tokens, but the idea is that you could, for example, then fine-tune on query document ID pairs, and that by training with this objective, you teach the model something about the document IDs and which document tokens are in the IDs, because the model has to learn to produce the document tokens, and therefore it might make some associations or something. I'm not exactly sure what the thing is behind, like what the reasoning is behind this, but you know, it's good to try. It doesn't work, turns out. There's also bidirectional, which both are done. So during training, there's like a multitask setup where sometimes you do the doc ID to tokens and sometimes you do the tokens to doc ID. Also in their experiment, the bidirectional method doesn't improve much over just the plain method. And the last one is span corruption, where you essentially input, I think, the tokens, and you append the doc ID, and then you consider this entire thing as like one piece of text that you want to predict, and you have this span corruption objective, which means that you can mark out any random spans in here between, which also means that sometimes you mask out the document ID or maybe part of the document ID, and that kind of forces the model to learn. It's a bit like BERT's masked language modeling, if I understand this correctly. However, also this doesn't seem to work super well for them, even though it has actually worked well in other tasks, so in other papers that have done things in the sort of sequence-to-sequence space. Okay, so now we have the indexing method of the table. The document representation strategies are next. The first one is direct indexing. They say we take the first L tokens. Again, this seems to work the best. Just take the first L tokens of the document. Interestingly, during the experiments, L bigger isn't necessarily better for L, which is also might speak to a little bit of the quality and nature of the data set itself, but also tells us, again, something about maybe this works in particular because we're dealing with sizes and data set sizes and lengths of documents that are actually possible to absorb into weights. And it is interesting to see how, as the data goes up, this becomes harder and harder. I would question, does it become like linearly harder to put this into a set of weights? Does it become exponentially harder if there's more data? Not sure. It would be interesting to find out. The other methods are, for example, set indexing, which deduplicates repeated terms and removes stop words. Doesn't seem to help much. And, naturally one might think that, if I remove stop words in my document representation, that gives me a cleaner signal. On the other hand, these models are pre-trained on actual language, not on cleaned up language without stop words. They're pre-trained on actual language. And therefore, I think they have a strong bias towards, kind of correct grammar and so on, and might work with that data a lot better. I think that might be largely behind why the direct indexing method works better over the set indexing. And then there's what they call inverted index, which is a bit in the spirit of how search engines classically do this. They say we randomly subsample a single contiguous chunk of K tokens from the document. So they're not only limited to the first L tokens, but they always kind of take a random substring of the document that is of that length. Now, technically, this should work better than the direct indexing. I like the inverted index in their experiment performs worse than the direct indexing, and I just don't believe it. It does not make sense, right? Something's going on. Either the data set is such that for some reason I can find a lot of the answers that I'm looking for in the beginning of the documents that are indexed, but this is purely a property of the data set, or it is really like the introduction of a tiny bit of noise into this, namely that for the same document ID, I see different substrings, I see different tokens. That already kicks the method out of its comfort zone. That seems to be in first instance, it's kind of a bummer that this is the data set, but we'll have to take it. In the second instance, it's a bit more worrisome if that were the case. Like if that fact would be already detrimental, where it actually should be beneficial. Or yeah, maybe I'm misunderstanding something, but it seems to me that this last method should be superior to the first one. So the next thing they investigate is how do we represent. By the way, I'm already telling you about the experimental results. They'll be coming up in the next section, but I think it's easier to mention them already here than to keep everything in your head and then go to the experimental results. But we'll go into it in just a bit. They investigate how should we represent the doc IDs. Again, the simplest thing you can do is to have these unstructured atomic identifiers, which essentially means that every document gets a unique identifier. And then in a sequence-to-sequence model, right, I have my sequence here. This is goes into my encoder, and then it goes into a decoder, and the decoder produces a sequence. Now, every one of those tokens is in a list, in a vocabulary. The vocabulary has a certain amount of entries. If I tokenize correctly, I have no out of vocabulary words, and this has some kind of a fixed size, like a vocabulary size. And the decoder, it can have the same vocabulary or a different vocabulary. In this case, I think it's the same. But what they do in this first method is they simply extend the vocabulary for the decoder, and the extra tokens here, every single token represents one document ID. This obviously only works if you know all the documents ahead of time that you're going to index, but in their case, they do. So they randomly initialize those embeddings, and during indexing, they train the embeddings for those. And that essentially means it's a multi-class classification problem. At the end of the day, every sequence prediction task is, but we're not going to predict multiple tokens. We're going to predict exactly one token, and that token comes exactly from this vocabulary. And that means this is not a sequence-to-sequence task. This is just a multi-class classification task. Now, this has advantages. Being multi-class classification, it means there's one prediction. There's no autoregressivity or anything like this. It's essentially a classic encoder-only problem. Though this is the easy part. The hard part is, of course, you don't leverage anything. You introduce a lot of new classes, a lot of new embeddings, and they claim in the experiments that these things are quite brittle, even though in the zero-shot case, apparently they work out super well. But we'll have some comments on that too. The next thing is naively structured string identifiers. So they say, again, like here, every document will have an arbitrary unique identifier, which is just kind of an integer. However, they just say, well, we'll just put the integer as a tokenizable string. So if the integer is like 1, 1, 2, 5, then the model needs to predict the tokens, like the strings 1, 1, 2, and 5. Or maybe it's tokenized differently, but it will actually have to produce this thing as a string, not as a output into an output classification bucket, but it will have to output the string. So this is now truly a sequence-to-sequence task, right? And the last thing they consider is these semantically structured identifiers, and where they think, well, can't we do something better for the document IDs? Like, can't we imbue them with some meaning? And they come up with the following procedure. So they have two principles they want to follow. They say the doc ID should capture some information about the semantics of its associated document. And second, the doc ID should be structured in a way that search space is effectively reduced after each decoding step. This results in identifiers where semantically similar documents share identifier prefixes. So essentially, they want the documents to have multiple, like the the IDs could be 255, which essentially means it's like a path, right? It's like a folder path. So this is supergroup 2, and then group 5 inside of supergroup 2, and then document 5 inside of that. And the assumption is that all the documents that are in the same like group 2/5, they share some stuff, such that the decoder, if it's not sure which exact document it is, but it can already say, well, in supergroup 2, I find all the things that talk about, I don't know, household items. And then in 2/5, there are all the things that talk about electric appliances in the household. And then inside of that, there might be some documents, but the model could consider step by step. The model would first consider outputting sort of the supergroup, and then condition on that in order to output the group, and then condition on that in order to output the next level. So that's what they do. They do a hierarchical clustering approach, which means that they take another model. So they take some sort of a, I think it's a BERT model. A BERT, I think. I'm not sure where they mention it, but they take a BERT model. They put all of the documents through the BERT model. They train and embed. I don't know if they actively train it or if they take a pre-trained one. In any case, they have some way of embedding documents. So they embed those documents. Then they use k-means clustering to divide them into clusters. If the clusters are still too large, they recursively subdivide them into clusters. And here you see exactly, so this here is document 233 because it's in supergroup 2. It's in subgroup 3, so that's 23, and then it's the third document inside of that, so that's 233. And presumably the 2 and the 3 the prefixes, they're kind of like the path into the hierarchy and make it easier for the model to decode. Now this seems like a cool idea, honestly, because it kind of makes sense. There are, however, two conflicting things. One is the fact that there is semantic meaning in 255 or 233 in that case, right? There is semantic meaning in these things and not just a random identifier. The other one is that it is in order. So the top hierarchy is first, then the second, then the third, which might interplay with the autoregressive way that we train these things. So in order to separate the two things, one would need to make an experiment where you just flip it around, right? You decode. While you decode, you decode from the back. You decode like 332, right? And then you essentially still retain the semantic information of the identifier, but you drop away the autoregressivity. So the model essentially could not condition on the supergroup while decoding the lower layers. So you could tease that apart a little bit. They didn't do that, but in any case, this would, I guess, be an idea of doing further ablation and understanding into how this model works. It is interesting. That's it essentially. Okay. Then how do they train? They say we try two strategies. One is to first train the indexing step. So first feed the documents and output their IDs, followed by a fine-tuning stage where you feed queries and map them to their IDs. Or the second strategy is to train them together in a multitask setup. That's exactly what we saw in the diagram. You feed documents and queries. For documents, you output their document ID. For queries, you output the corresponding document ID. And you have some ratio of how many indexing samples and how many query samples that go in. Turns out that second method is better, which I don't know if I would have guessed that, but yeah, it kind of makes sense because it's cleaner and you can essentially scale and distribute. There's no ordering effect. There's no catastrophic forgetting or anything like this. And And yeah, so that makes sense. So that's what they do. All right, we'll get into the experiments now. The dataset is natural questions. This is a question answering dataset, and it can be used for retrieval because the dataset essentially always contains a question, a passage, which is usually called the context, and an answer. This is one data point. Now, the idea is that you look at the context and the question and you find the answer inside of it. However, you can make a retrieval dataset out of this by forgetting about the answer and by severing the connection between the context and the query and considering the entire dataset. And essentially the task is now, if I have a given query, a given question, which context is the correct one to go with that question. So you can make a retrieval dataset, which is usually quite hard because the dataset is made with the fact in mind that you will get the context, right? So it is not necessarily the same as a user typing something into Google, where they need to look for a document. The question is a question about the document if you already have the document. So it is a little bit, it is an okay data set for retrieval, but it's just not a direct retrieval data set. Also, note that it's kind of like 300, there's 300K data points. They make subset of that. So they make a 10K, a 100K, 10K data set, a 100K data set, and a 300K data set. So a small, medium, and large. Although even the large one, right, is not very large. You can, because in a search task, 300,000 documents, it seems a lot, but if you build search applications, that is not a lot of documents, right? A lot of document collections have millions of documents and more that you need to retrieve from. But it is good to observe scaling properties right here. But just keep in mind that their largest data set is still not super duper large. The other thing you can see, they have train pairs and validation pairs. And that kind of, yeah, so all of these things, they have a special notion right here, which I'm not exactly sure, I have to be honest, how this is exactly done. So the training pairs, I have the queries and the context both, right? And for the validation pairs, I also have queries and context. Now, usually I train a question answering system. I train on these things, right, with the answers. And then I input these things over here at inference time. However, if I train a search index, I certainly need to index at least the contexts of the validation pairs. And I simply prohibit myself from ever seeing the queries. So what I think they do is I think they take these together. These are all the contexts, all the documents, and they take the queries from the training set, and that makes sort of the quote unquote training set, right? This here would be indexing, and this here would be fine tuning. And then they evaluate, this here would be eval. But this is a hypothesis of mine. I'm not exactly sure that that's what they do, because certainly they can't just not index the data that they're going to retrieve from, right? But I hope they don't actually fine tune on the queries that are in the validation set. But again, maybe they also first do this, and then as a last step, they then index the validation set. I'm not sure, just honestly, and I couldn't read from the paper. Maybe I've overlooked something, but it would be a good question to the authors how this exactly is done. Training regiment seems pretty decent. So it's Google research, so they have the big chips. Yeah, T5 isn't exactly a small model, right? Especially the larger ones. So here are the results. And they are all over the place, which makes me a little bit skeptical. First, you can see in general, the larger models for the differentiable search index generally outperform the smaller models by a lot, right? You can see here, for example, these are large models, these are small models on the same task. These are hits at 1 and hits at 10, which means if the correct answer is in the top 1 or the top 10 respectively. For all of the DSI models, that's the case. By the way, when it says T5 here, that is a dual encoder baseline, and above here you can see the BM25 baseline. Now, also, I would like to draw your attention to the fact that BM25 on the small data set, it gets like a performance of 12.4. On the large data set, it gets like 11.6, which, you know, is reasonable. It kind of goes down a bit if the data set is larger because it can confuse the documents a bit more, but in general, it's constant. But then there's like a big jump in this 100K data set. Like, what's up? What's up with that? This seems to be weird. So you can't really see that in the dual encoder setup. There is a jump here, but that remains. Then if you look at the small models here, it goes up and it goes down again. Yeah, that's the same trend. But then here, if you can see, it kind of goes down in performance and then it goes up. No, it kind of remains down. All I'm saying is this might be to be expected. This might be expected because going down in performance is what I would expect if the data set becomes larger. Okay. But there are some inconsistencies among here. Yeah, all the weirder that here it actually goes up. And as you can see, the highlighted bits right here, for example, this thing, the methods that work, they seem to be all over the place. Sometimes this naive string docid is the best. Sometimes this semantic string docid is the best. The clear trend is that pretty much everywhere the larger models are better, which I think is reasonable to say because they're going to have more capacity of adopting the data into their weights. And in other trends, the larger the data set gets, the worse the models become. Again, like, look at this. It goes down, to be expected. It goes up again. What's up? So this data set is cursed. So we won't look at it. So let's just compare the very left and the very right things. You can also see that there is a big improvement over BM25, which is surprising, right? That even the dual encoders improve over BM25, but this differentiable search index, especially if it gets large, improves by quite a bit. Now, I suspect, again, that is kind of the nature of the data set right here, but it might as well be that all the embedding techniques are very good. But yeah. Lastly, what I want to point out, the improvement over the dual encoders of the differentiable search index, so over this baseline right here, this gets smaller and smaller as the data set grows, right? Which we discussed at the beginning and which I think is a little bit of a bad sign for these types of techniques in that obviously as I have more data, I cannot really save it into my weights as easily. And the dual encoders, they are not like the embedding space, high dimensional embedding space is kind of infinite, right? So I can save a lot of stuff there no matter how much data I have. It'd be interesting though, because there are techniques in which you can, like if I have a matrix and I want to store stuff in that matrix, as long as I build like low rank matrices that I add to it, or in vector terms, if I build like vectors that are largely orthogonal to one another, I can, save a lot of stuff in a single matrix by just adding to it, or to a vector space or to a set of vectors. And maybe, with a bit of trickery in how the weights are updated exactly for the different documents, one could improve this quite a bit. This here is the zero shot setting, which means this models, they never see any queries. They never learn to map queries to document IDs. They simply learn to map documents to doc IDs, which is an additional difficulty. Again, you can see that the weirdness of BM25, right? That's exactly the same, right? BM25 is going to perform the same because BM25 is always zero shot. It never sees labeled queries. You just can't. I mean, I guess you can also run it through indexing, but yeah. Interestingly, the dual encoder in a zero shot fashion just sucks. It really sucks. The sentence T5, which is explicitly made for like sentence similarity, it is apparently okay. It apparently outperforms BM25. Also, I have trouble believing that, but if they say so. But then these DSI, they really shine in this, especially here, this atomic doc ID method. For some reason, it really is really good. As you can see, it outperforms the semantic string doc ID, which was kind of the best one before, or one of the best one. Also, this naive string doc ID was really good before. It outperforms that in a zero shot setting. So the results are kind of all over the place. And that is what worries me a little bit, in that it seems to be quite noisy. They themselves admit or report that training with these atomic doc IDs seems to perform well in the zero shot setting, but it's also quite unstable. So yeah, it's a cool method, cool paper, and it shows some really interesting results, but it also seems that there's quite a bit of noise, and probably we haven't exactly figured out many of those things yet, which is a good thing if you're in research. Yeah. So they find a bunch of things, like in general, they say structured semantic identifiers are helpful and improve over unstructured ones. However, we also note that unstructured atomic identifiers perform the best by a wide margin on the zero-shot retrieval setup. Who knows why? I guess we can hypothesize. The other methods I've already discussed a little bit, especially model size. It seems to be really important, as you can see. For dual encoders, that doesn't make super duper difference. It makes much more difference for the differentiable search index. Whereas if you talk about dataset size, a higher dataset size seems to be much more detrimental to the differentiable search index than it is to a dual encoder. Interestingly, also, the length of the tokens you index per document seems to be better if it's kind of shorter, which is interesting. So if you index the same documents for longer, for more tokens, that seems to hurt performance. And really, if you go much, much longer. And lastly, here they investigate how much indexing versus retrieval they have to feed in during the multitask training. If they train index and labeled query pairs at the same time. Turns out that's also fairly noisy, but you can't go too high. One seems to be fine, right? So you can get an improvement if you have more indexing, but one seems to be fine, which is already relieving. I think you could just mix them together and you'd be fine. Yeah, I wanted to say one more thing. Yes, so in their conclusion, they talk about document identifiers, and they say it would be interesting to explore alternative strategies for representing documents and doc IDs, including end-to-end strategies for learning semantic identifiers. That's what they say, because they're kind of unsatisfied with the way they represent the document IDs, because the height of their method is this hierarchical clustering, which is also, it uses a separate encoder and so on. However, I'm thinking myself, if you want this to be learned like end to end and so on, isn't that exactly like regressing to cross encoder setup and dense retrieval setup? Isn't that essentially what you're doing if you're learning these things end to end? I don't know exactly how then that's going to be different in principle. And this is a little bit of my worry about this paper as well, that they didn't compare at all to any cross encoder setup, to any kind of re-ranking setup that are very prevalent in neural search these days, any dense retriever setup. Maybe dense retriever is by encoder, I'm not even sure. But I feel these are some baselines that are missing right here, along with the smaller size of the data set. But all in all, pretty cool. Again, I don't think this is necessarily going to be such a use in search in itself, like search through document collections, but much more could be very useful as a part in, for example, a reinforcement learning agent who has to store stuff during the episode and then retrieve it later in a very differentiable manner, in an addressable manner. It would also be interesting to see, whether outputting document IDs is better than outputting the information that I want directly, right? Because you could also think of that. You could also say, here is a query, just output the document itself or the part of the document that matches instead of outputting the document ID. How does that perform? It would be equally interesting to see that. So lots of things to research. I really like this paper because it does something different. It does something weird, and it puts in the engineering effort to figure out what makes it work and what doesn't. And that's it. Let me know what you think in the comments. I'll see you around. Bye-bye.